The broadcast is now starting. All attendees are in listen-only mode.
Hi, everybody. This is Vivian Silva from the Weather Program Office, and welcome to the Weeks 3 and 4 S2S webinar series. Today, I'm covering for Carrie Keith. And for this webinar this month, we have two speakers. We have Zane Martin from CSU. He's going to be talking about using simple machine learning models to predicting the Madden-Julian oscillation. And we'll be followed by John Gottschalck from the Climate Prediction Center, where he's going to be talking about the CPC Global Tropics Hazards Outlook. So before we start, you all got in the invitation, this is our webpage, and just a few things that I would like to point out. If you'd like to subscribe to receive notification about this monthly webinar, you can just click here in our page. And also, if you have interest in speaking, you just can fill out this Google form, and we are going to be following up with you. And if you want to see the previous webinars, you can just come here in the site, and we have all the presentation recorded and available to you. So before we start, also, we have in the invitation email, there was a link for the discussions, and we have included in the chat the link. So if you have any questions during the presentation, could you please just type your question in that for Google document, and the speaker is going to address if we have time, and if he does not, he's going to follow up with our response, and we'll make sure that everybody has access to that response. So we've said that, I'm going to be passing the word to Zane Martin, and I'm just going to make him a presenter. So just a minute.
I would also like to remind everybody that we are recording this presentation as well. Thanks.
Okay, great. I think you should all be able to see that that slide. I guess let me know if there's any hiccups along the way. But otherwise, I just wanted to thank everyone for joining this afternoon and giving me this opportunity to talk about some of the recent work that I've been doing at CSU. This is work alongside Libby Barnes and Eric Maloney, who are both faculty there. And it's really about trying to use simple neural networks, which are a machine learning tool, in an explainable way in order to further our ability to understand and predict the Madden-Julian oscillation. And my portion of this project has been funded by NSF, and both Libby and Eric have been funded by NOAA for their contributions towards this work. So I thought it would be fine to sort of give a relatively quick overview of the Madden-Julian oscillation for this audience. I think many, if not all, of you working in the S2S space are probably aware of what the MJO is, but it's the core of my talk today. And really, in essence, the MJO is this major mode of subseasonal to seasonal variability in the tropics and a source of global S2S predictability around the world. And the key characteristics of the MJO are its planetary scale and its eastward propagation. So you see in this video here, this animation, MJO rain signals. The blue is increased and the red is decreased rain relative to some background state. And these signals form in the Indian Ocean, and then they move slowly to the east out over the maritime continent into the West Pacific. The MJO also has wind signatures. It modulates a number of different variables in the tropical atmosphere. And the only other thing I want to highlight on this slide is if you look in the top right, you can see Rmm Phase. And what that means is that's an index. Rmm is a way of measuring the strength and activity of the MJO. And the phase describes where the MJO is in its life cycle. So you see like phase 1 and 2 have active rain over the Indian Ocean, phase 3, 4 over the maritime continent. And then, phase 7 and 8 describe MJO sort of decaying over the West Pacific. So those 8 phases are an important way that we talk about the MJO that will come back in a moment when I get into the details of my talk. So in general, predicting the MJO is a big part of successful S2S predictions because the MJO is such an important source of, again, predictability on these timescales in the atmosphere. And I thought I would give a brief overview, a kind of snapshot of 2 parts of MJO prediction, 2 kind of ways of doing it, and where the science is kind of today in these two regimes. So the first is a statistical modeling approach, and the second is what I'm calling a dynamical modeling approach. And of course, this dichotomy that I'm introducing is artificial, right? Of course, there's lots of statistics that go into dynamical modeling and you know, vice versa. But I think it's useful to kind of frame the overall sort of problem of MJO prediction in this way. So statistical models, really, I'm just talking about empirical tools to predict the MJO that, given past relationships between, you know, certain aspects of the oscillation, make predictions about how the oscillation might behave in the future. And in general, this used to be the kind of state of the art with MJO prediction, and has sort of fallen by the wayside. These statistical models tend to show skill out to around 2 weeks. There's a wide range of different approaches in the literature to doing this. I want to emphasize that most of those methods are linear, both in terms of how they process their data and how they make their predictions. In contrast, dynamical models are increasingly, I think, the state of the art in terms of MJO prediction. They show skill, the best ones now out to, you know, up to 5 weeks. And really a lot of that has been driven by improvements in these models since sort of the mid 2020, sort of 2008 or so. So we understand the model processes better. We're putting more effort into this, you know, growing ensembles and doing model intercomparisons. And really this sort of dichotomy is where our work started. We wanted to understand a future of statistical MJO prediction. And in particular, you know, we were looking at the rise of machine learning as a tool across the earth sciences for everything from, you know, ENSO prediction on a seasonal time scale to people that are incorporating machine learning into climate models to try to improve things like parameterizations and so on. But we felt like, you know, a deep understanding of how we might use these methods to predict the MJO was lacking, and I think it's important to begin to address, you know, how these tools might be useful in this kind of S2S space and understand their strengths and their weaknesses. So really, we're focusing on using machine learning to predict the MJO in a statistical sense. We're not, in this work, using it as a sort of like post-processing for a dynamical model or something like that. That's a whole other area of research that is active that I would be happy to sort of speak to, but it's not really the central part of this work right now. So in general, I don't want to get too much into the weeds about how machine learning works, but I do think it's, you know, it's worth at least giving a brief overview of some of the advantages of this method and a little bit of the terminology. So machine learning is really good. This is a really simple way of thinking about it, but this is kind of where this project started. It's good at getting from A to B. That is, it's good at learning relationships between some predictor A and some predicand B. And a lot of setting up a good machine learning problem is, one, having a lot of data, and two, being careful about, you know, what you choose for this A and this B. So the simplest, like a traditional linear transformation that you might think of to get from some predictor to a predicand is just a linear transformation. You take your input, imagine it's some vector, you could multiply it by a matrix, and, you know, you could add another vector to it, right? That would be, depending on that matrix X, a straightforward linear transformation. But one of the strengths of machine learning approaches is that they incorporate non-linearity. So if the relationship between A and B is not linear, they can learn those functions. So they're much more powerful tools, again, if you have enough data, at learning kind of complicated relationships between inputs and outputs. And so I just want to highlight, incorporating this nonlinearity. You see in the bottom right a function which is called ReLU. That's the sort of parlance in the machine learning language. It's a nonlinear function that just takes, if x is a positive number, it just returns that number back. But for all negative numbers, it returns 0, right? And so as you're doing your data transformations within your machine learning model, you pass some linear transformation through that nonlinear function, and it incorporates, that sort of more complex relationship. I also just want to stress that, unlike something like a linear regression line where we have a sort of really clearly defined, we know what the best fit line is in a rigorous sense. In machine learning, we often don't know what the optimal mapping from A to B is. And so machine learning models iterate basically over what's called training data. And so they're constantly assessing basically how skillful their predictions are through what's called a loss function. And then they're updating themselves in an automated way, such that ideally the next prediction is better than the first. And so by iterating many, many times over some large training data set, you can basically build a model that learns to minimize this loss function and hopefully make skillful predictions. That's a very high level overview, and I'm happy again to get into details in the questions, but I think it will give you a sense of how we're thinking about this. So now that maybe that arrow is at least, in theory, a little clearer, I want to talk about how we've actually set up the problem for the MJO. So what we're going to input into this model are maps of tropical variables, 2D maps, and we're going to choose important variables for the MJO, things like wind and convection and so on. And I want to highlight that the way that we're pre-processing our input data, we're removing a seasonal cycle like a climatology, and also removing longer term variability with a 120-day mean. But we've processed our data so that we can do these forecasts in real time. So there isn't any bandpass filtering or anything like that. We wanted to explore the kind of real-time application in this first project. So we're going to give it these real-time maps. I'll show an example in a moment, and then we're going to predict an MJO index, which is that real-time multivariate MJO index, the RMM from that very first video. So RMM is basically a concise way of measuring the MJO, and it has strengths and weaknesses, but I think an advantage is that it's very sort of used across all different statistical and dynamical modeling. So it's like a good starting point to sort of benchmark or contextualize our results. Again, there's a lot of flexibility to change both the input and the output, but I think, this being sort of a starting point for this branch of work on MJO prediction, this felt like the most sort of logical beginning to us. And I'm going to talk quickly about two different frameworks that we've set up for MJO prediction. One of them is going to be deterministic. I'll talk about that first. And then the second is a probabilistic machine learning framework. And they're similar in many regards, but we did want to highlight the kind of flexibility of these methods to do both of those types of forecasting, and also wanted to understand, are they comparable to each other? Does one outperform the other? So you'll see both of those as I go through. So this is a bit more information about this first deterministic model. It's called a regression model. That doesn't mean it's a linear regression. That just means that it's outputting basically numerical values. So you see on the left these input maps that I talked about for 3 different variables, and almost all of the results I'm going to talk about are models that take these 3 inputs: the outgoing long wave radiation, and then the zonal wind, U, at 850 and at 200 hectopascal. So at the upper and lower right branches of the parts of the troposphere. So each day we have one of these maps, and we concatenate that, and that's our input into the model. And then we have one hidden layer that basically is describing how many of these nonlinear transformations we have within this machine learning framework. And without, again, getting into the details, essentially we have a relatively simple machine learning model here. So you can add many, many layers. You can add many more nodes, which is basically the number of transformations per layer. And in the sort of world of machine learning, this is a very simple model to have a single layer with 16 nodes. But we found that given the data that we have, this model performed, we wanted to choose the simplest model that we could. And this is about where we kind of found, through sensitivity tests, what we found optimal. I also want to stress that all of our data that we're using to train and validate is all observations for this, observations or reanalysis for this study. So our OLR is the NOAA satellite OLR, and then our zonal winds are coming from ERA5 reanalysis. And people have moved to climate model data, and that's, again, something we could talk about. But for this study, we wanted to just focus on the observed data set. So we're going to use the first 30 years of the record as our training data. That's the data that the machine learning model is going to see over and over and over again as it's finding this optimal mapping between our input and our output. And then we're going to validate on, basically do what amounts to like a hindcast experiment from January 2010 to November 2019. So we have 10 years on which we're validating our model on data it hasn't seen. And again, this first model is outputting the values of RMM at different lead times. So we have different models that do, a lead of 1 day, 2 days, etc. So we're inputting maps and we're outputting RMM, and we have different machine learning models for each lead time trained on observations. That's kind of the concise way of summarizing what it is that we're doing. And so the first thing that we wanted to understand is just overall, from a sort of 100-foot perspective, what's the skill of this model? So I'm just going to talk about the skill. We trained the model in winter and in summer separately. Winter here is October through March, so it's maybe a bit broader, but it's that 6-month chunk. And I'm going to focus on winter just to be concise, but the overall results are not hugely different from one season to the next. So this plot shows the skill in winter. Skill is on the y-axis, and it's the correlation between our predicted MJO indices and the real observed indices. And we use this typical threshold of 0.5, so this black line denotes skill. The gray lines are either very simple linear statistical models. So there's two that are used in the literature here. I won't get into the details of them, but they're linear models that use RMM to predict RMM. And then we have a simple persistence model. And you see that the machine learning model outperforms these traditional statistical techniques. And it does so modestly, but it shows around 4 more days of skill out to around 17 days, as opposed to the kind of 13 to 14 days that, again, traditional linear techniques show. So we're performing better than the linear models, which is exciting, but I do want to emphasize, and I'll come back to this at the end, we're not really competing with these dynamical models that are showing skill out to a month, at least in this sort of preliminary and simple, machine learning setup. For those of you that study the MJO, we dove, a little more into kind of the details of this model to try to understand, whether it was showing behavior that was consistent with literature on MJO prediction. And these are two of the more interesting plots, I think, from that work. So basically what these are both showing is, again, these are skill plots as a function of lead time from this model. And I'm showing the sensitivity to initial conditions. So the different lines are the same model. I'm not retraining any machine learning model. All that's changing is what initial conditions we're using. So on the left, we looked at binning by the initial strength of the MJO. So the red lines are strong or very strong MJO events with amplitude greater than 1.5. And you see that in that case, our model has skill out to approximately 20 days, which is quite a bit better than the overall skill, versus the weak MJO events. So when the MJO isn't very active, when the RMM index is less than 1, we only have skill out to around a week. And this is consistent with literature on the MJO, but it gives us confidence that our model has learned the MJO signatures, right? It's learned sort of to take these strong events, and that's where the signal really is. The plot on the right is a little more interesting. It shows the change in skill to the sensitivity and skill with regards to the stratospheric winds. So the stratospheric winds change between easterly and westerly. It's this oscillation called the quasi-biennial oscillation. And in the last few years, there's been a lot of work showing that the MJO actually is more predictable when these stratospheric winds are easterly than when they're westerly. And we don't really understand why or how that relationship works yet, but it's a sort of evolving area of MJO prediction. And so when we look in this model, with the caveat that we're validating only over 10 years, so we don't have too many of these, the quasi-biennial oscillation, right, is cycling every 2 years. So we don't have a huge sample size. But nevertheless, you do see that when the QBO is easterly, this green line, we see increased skill out to around 20 days compared to when the QBO is westerly, where we get skill around 14 days. And I want to emphasize the machine learning model knows nothing about the stratosphere, right? We're not giving it the winds. We're just giving it those zonal winds at lower levels and the OLR. And yet it's somehow able to leverage that and still find higher skill in these different states of the QBO. So there's some I think evidence that these machine learning models are doing, they're learning nuanced aspects of MJO behavior that we're interested in perhaps diving into more and understanding in future work. I'll briefly now talk about the other framework that we set up. So this was, I said there was a deterministic and a probabilistic. This is our approach to doing probabilistic MJO forecasting. So in general, the setup is very similar. We're inputting the exact same, right, daily anomalies. The model architecture, in the sense like the number of nodes and layers, is the same, although we're retraining the model from scratch. So the machine learning model is different, though the overall kind of complexity of it is the same. Really what we're changing in this case is what the model outputs. So rather than outputting numbers that describe an MJO index, we're outputting the probability that the MJO is in one of these 8 RMM phases, or the probability that the MJO is weak. And so to make this a little more concrete, I'll just show an example of one forecast. So on the top left is a phase diagram of this RMM index. So you plot, basically the index is 2 numbers, and you plot one against the other in this kind of 2D plane. And in this space, the MJO kind of traces out counterclockwise circles. That corresponds to eastward propagation. So you see that if this is the lead 5 prediction, so a model that's optimized to do 5 days in the future, you see the initial condition here is this red star, and then right? 5 days after that, the MJO is in what's called phase 7. And the forecast from the actual model, right? This is the output from that one forecast is on the right. You see the model says it thinks there's a approximately 56, 57% chance that the MJO at a lead of 5 will be in phase 7. It's correct in this particular example. But you can also see that, right, the model is smart enough to realize that there is some chance that the MJO may be in phase 8. So, right, we're right on the border of these phases, and it says there's a 22% chance that we could have a phase 8 MJO 5 days from now. Another interesting thing, right, is that you see that the model is, at least in this example, but this is true overall, the model doesn't tend to do very poorly in the sense that, you know, it realizes there's a very little chance that I'm in kind of phase 3 or 4. You know, it's able to get it usually within one or two phases. So this probabilistic forecasting approach, we thought was it's not done as much in the simple, you know, the simple statistical modeling world. But there's some cool things that you can start to look at. So this is just one example. We looked at how the model's confidence, how that like probability that it makes, how that relates to the accuracy. So on the x-axis here, you see basically I've binned forecasts by their confidence, and I think like 5 percentage bins. So, you know, 60 to 65%, 65 to 70, and so on. And then the accuracy is shown on the y-axis, on the one-to-one line of these black X's. And what you see overall is that in general, in particular at short lead times, as the model gets more confident, the accuracy goes up. And in fact, you know, at certain lead times, the sort of reliability of the model, you know, the sort of relationship between accuracy and confidence is quite good in the sense that, you know, here at lead 0, when the model is 75% confident, it's about 75% accurate. At longer leads, the model tends to be a little overconfident. So, you know, at a 50% confidence, it's accurate maybe around 40% of the time. But it does mean that, you know, if we wanted to say, look at only the most confident forecasts, the model is more skillful in those cases. And there's folks in our group that are looking at things like forecasts of opportunity to try to sort of, you know, continue to leverage this kind of probabilistic information. I'll also just highlight that you can measure skill of the probabilistic forecasts. It's done a little bit differently. We essentially come up with we use what's called a ranked probability skill score and compare this model to something like a climatology. So here, where the values are greater than 0, the model is basically more skillful than just a climatological probabilistic forecast. And you see that the ANN in purple has skill out to around 15 days as measured by this metric in winter. And so again, that's consistent in general, although it's quite a different model with the overall skill that we found in the regression model. You know, skill seems to be on the order of between 2 and 3 weeks. So that's, I guess, sort of the first part of this work. And I just want to spend a few minutes looking at this second question. So I've really talked about skill and focused on, you know, prediction skill as the kind of be all and end all of these ANNs. But we have started to think harder, you know, as we've gone through this project about, can we use these ML tools to move maybe beyond just prediction? You know, are they useful in their own right as ways to study and understand the MJO? Or is machine learning really just about, you know, optimizing predictability? And in this study, we kind of make the case that there may be ways to start using these machine learning models, you know, in addition to just assessing them by their skill, to use them as tools for understanding. So I'll give kind of 2 sort of preliminary, like, proof of concept ways that we've thought about this problem, and I'd be interested to get other thoughts or feedback. So one thing that we realized that these models were quite good at is they're very efficient. You know, you can run this model, you can train it on a single computer in a couple of hours, and to do a single forecast takes, you know, a second. So we spent a while looking at giving the model different input variables and trying to understand, you know, could we get different predictability as we gave the model different variables, right? Were there certain sources of predictability coming from certain variables that we could leverage more? So this plot shows the accuracy of the model predicting the active MJO events at 3 different lead times, 0, 5, and 10 days. And the different colored bars are different combinations of input variables. I'm not going to get into the details. I know this legend is kind of it's a bit intimidating if you don't, you know, if you're not up on the sort of, you know, P's and Q's of what different atmospheric variables mean. But this blue bar, for example, is the OLR and then the zonal wind model that I've been talking about. So you see that's sort of a good benchmark. And I'll just give 2 examples. So you can see a model, this green bar, where we give it the OLR and then the moisture at low levels, that's Q, and the meridional wind at low levels. That green bar tends to underperform compared to the zonal wind and OLR model. So the model really is using the zonal wind as part of making its predictions. And that makes sense because RMM is quite a sort of circulation-driven index. But you can also see, for example, this gray bar, which is total column water and then upper level wind and temperature, performs pretty well at leads of 5 and 10. So even without the lower level wind, if we give the model information about temperature at the at the upper part of the troposphere, it's able to leverage that information to make skillful predictions. And so I think one avenue that we're exploring for future work is looking at giving the model even more nuanced input. If we give it something like maybe moist static energy or more sort of processed variables, can it kind of pull prediction skill out of those different inputs. And then the last point that I'll make in the last minute or so is that there's a whole host of tools that exist that are in this field called explainable artificial intelligence that are trying to help scientists understand how these very complex nonlinear machine learning models work. And so this is a particular tool that our group likes called layer-wise relevance propagation, which you can use on neural networks, that really tries to demonstrate what aspects of an input are most important for making a prediction. So this is from a website, the link is here, that uses LRP. Basically, you upload images, and they have a machine learning algorithm that tries to tell you what's in the image. And so I uploaded a RAM because I'm at CSU, and you can see that the machine learning model, identifies this as a RAM. And this plot on the right is the interesting part. This is what the LRP algorithm returns. It's a heat map, and the darker reds here, show you where in this input did the model look to say this is a RAM. So you see it focused on the eye, on the horns, and on the nose here. And we can apply this same technique to the MJO. So that's what we've done in this plot. This is looking at the correct model predictions for a phase 5 MJO event at a lead of 0 on the top and a lead of 10 on the bottom. And these left panels are the OLR input into the model. And then the right panels are these LRP relevance maps that are highlighting where in these inputs is the model looking to make its prediction. And what you see is that essentially the model, so the way that we've used this tool to date is basically to convince ourselves that the places we as domain scientists would look are the places that the model is looking. So for a phase 5 MJO, we would expect active convection over the maritime continent and suppressed convection over the Indian Ocean. And you see that those are the 2 regions that light up at the lead 0, That's where the model is looking. And then at later lead times, the model is learning to shift where it focuses. For example, at a lead of 10, it's looking at the active MJO convection in the Indian Ocean and learning that that's then going to propagate, to the east in 10 days' time to set up this phase 5 condition. So that basically demonstrates, using LRP to understand, how the model is working. But I think there's work, we're looking now at trying to look at, how do these maps differ, say, in different large-scale states, or can we use LRP to understand what are the sources of MJO predictability in our inputs, and how does that relate to things like model confidence or particular case study forecasts? So I think I'll leave my conclusions up. The first part of the talk, I talked about prediction, and I showed that while we outperform traditional statistical models, there is still definitely room for improvement for machine learning to catch up to the kind of state of the science dynamical models. But I would argue that just looking at prediction skill is perhaps giving these ANNs short shrift, and that in general these are flexible tools that in conjunction with these AI methods, I think might be useful as a sort of another tool in our toolbox for looking at and understanding the MJO. So I'll leave you with that, and thanks so much for listening. Look forward to answering y'all's questions.
Thank you, Zane. This was a great presentation. So it's almost 2:30. So there are 2 questions on the discussion forum, and if you could take some time and just to see if you address that, and then we can move to John Gottschalck just to make sure we'll be on time. So.
Sure. I can't see the questions. Do you want me to do that now or just respond in the?
Yeah, if you can you open that discussion forum? And
yeah, I see it. Yeah.
And you can just answer there, maybe with different color or something.
Sure. Yeah, I'll go ahead and do that. Thanks so much.
Okay, John, you can take over.
Okay, can you hear me okay, Vivi?
Yes, we can. Thank you.
Okay, great. Thank you. Thanks for the organizers of the seminar series for giving the opportunity to speak this afternoon. My topic today is going to be on somewhat similar in the sense of a phenomena that Zane was talking about, where the MGO plays a large role in the particular product that I'm going to be talking about today. I'm going to be providing an overview our current operational products and of the global tropics hazards outlook that we produce at the Climate Prediction Center at NOAA, and how we're working towards transition that to a probabilistic format targeting the week 2 and 3 time period, which is more in line with CPC's mission and goals. And I want to definitely acknowledge that the majority of work that I'll be presenting was done by Lindsay Long and Nick Novella, that are also colleagues of mine at the Climate Prediction Center. So going into the outline, the first section will be just general background and overview, so everyone is familiar for those who are not about the product. The second will be generally the transition or viewing of what the new product will generally be formatted in and appearance, at least at this stage. And then the last section, which will be the majority of the talk, will be on some of the applied research and development tasks and results that we have with some of the information, forecast guidance, and statistical hybrid type tools to inform the new outlook, both for precipitation and tropical cyclones. So the first section, some of the background is that CPC, as I mentioned, has been releasing the Global Tropics Hazards Outlook once per week. It's released on Tuesday early afternoon or mid-afternoon Eastern time, although we do have an update that we produce for the Northern Hemisphere hurricane season for the Eastern Pacific, Western Pacific, and also the Atlantic basins on Friday afternoon. This targets the week 1 and 2 time period separately, week 1 and week 2 separately, and the outlook depicts hazardous areas for either enhanced or suppressed weekly tropical rainfall, mean temperature, as well as areas in which tropical genesis may be favored in the various ocean basins across the globe. The products are right now generally currently categorical with respect to confidence. They're limited in subjective manner as the approach to date. As far as reasons that NOAA does this and why this is important to move forward is that I think, as many folks would agree, commerce, economic stability, and many other factors, food security, for example, are global in nature. Many sectors of the U.S. economy have international links, requirements, and interests in these types of areas. And the product supports NOAA and the Weather Service, National Weather Service, and other federal agencies by assessing and evaluating the current forecast distribution of anomalous tropical convection, which aids in our communicating advance notice of any potential pattern changes to the National Weather Service field. We also provide a subseasonal tropical cyclone outlook for U.S. impacted areas, and this applies and feeds into additional information for U.S. national security interests, especially for the Department of Defense, aid organizations such as the Red Cross, and other global operations that have interests in these sort of sectors. An example of the product as it is now is shown here, which the top panel or top figure is for a week 1 time period, and the panel below that is for a week 2, the week 2 time period. What's shown in green are areas in which we've favored in the forecast above normal precipitation on the weekly totals, and yellow for below normal precipitation in weekly totals, where the red areas indicate favored environments for potential tropical cyclogenesis and associated impacts. The striping is indicated more of a moderate confidence. Again, that's subjective in nature, and the full shading or the solid shading is indicated for more of a higher confidence. And you can see in the legend below those areas, as well as temperature, which does not happen to be on this particular forecast map. Along with this, we produce a text discussion explaining the rationale behind the forecast, why the map looks the way it does, what's impacting, what are the main factors, how these forecast patterns are going to result potentially in any hazardous conditions in the tropics, but also how they may relate to circulation changes and potential changes to the mid-latitude circulation, and therefore impacts potentially to Alaska, Hawaii, and the U.S. Contiguous United States. These forecast maps are available for other disciplines via GIS and Google Earth formats as shown in the right each week when this is released. There's quite a bit that goes into the preparation of that particular forecast map that's shown. This is kind of a quick schematic that shows the larger scale down to the more final scale approach or paradigm that we make use of. The forecasters make use of at CPC each week. We certainly know that sometimes we have background low frequency base state conditions related to ENSO. For example, whether we're in El Nino or La Nina pattern or if we're in ENSO neutral conditions. And then as we get further in as a baseline, and then as we get into more of the subseasonal, we know, as Zane mentioned, MJO plays a large role in the interseasonal time band for various impacts in the tropics. And so knowledge of those impacts and also forecast and current assessment of where how strong the MJO is, how coherent it is, and also what phase the MJO is, plays a large role in the outlook. There's a number of different simple empirical tools that you can use to provide a pretty good first guess for what conditions will be like over the next 1 to 3 weeks, just knowing the current phase of the MJO and its typical impacts if it is currently active. As we go further down, we start to have to include other information that's become that's also very important in this week-to-week variability, which are other modes in the subseasonal range that are coherent, that can be monitored and there's a deep understanding of that in the literature. These are atmospheric Kelvin waves, for example, equatorial Rossby waves, and of course, African Eastern waves, for example, with respect to tropical cyclones. This information is included as well as other interactions between the mid-latitudes and then in the subtropics, such as low latitude frontal activity, blocking, for example, atmospheric wave breaking type of patterns and events are something we have to be aware of as well. And all this information in our own understanding is also worked into a number of dynamical model guidance forecast tools that we make use of for both precipitation and tropical cyclones, as well as statistical and hybrid type tools for precipitation and tropical cyclones, as I mentioned. And all this information feeds into the eventual outlook maps that are drawn by the forecaster with first guess information as best as we can based on objective information from all the different tools and factors that I mentioned above here. So one of those, I won't spend much time on this because Zane covered the MJO very well. The only thing I want to say with this is that on the plot on the left is a time longitude diagram of 200 hectopascal velocity potential anomalies. And this is actually during the dynamo period, dynamo campaign. Some of you may be very familiar with that it was, that took place between later 2011 into 2012. And I really note this in that this is kind of an example in many ways of some of the factors that we have to deal with from an operational point of view on a week-to-week basis, where the flavor and character of MJO activity, if it's active, can be quite different. And for those of you who remember, during the dynamo period, there was a lot of activity, fortunately, a lot of MJO activity. What's circled here is kind of a more, these lines that are sloped here, these dashed and dotted lines indicate somewhat more faster movement on the lower end, if you will, of the MJO time scale. And you can see how that was pretty coherent for a number of months in October into November. And then later on, during February and March of 2012, the character changed somewhat. The MJO events were slower as far as their phase speed, much more zonal in scale. Some of the anomalies, as shown in the bottom part here, the sloped lines, if you will, are a little bit less horizontal. And you can see the periods of enhanced convection indicated by green and blues, and suppressed convection indicated by browns and yellows last considerably longer. So it's these sort of characteristics that impact the week-to-week variability for the outlook. It can be very, very challenging. As far as predictions go, we certainly use the observationals as a one way of having a very good predictor, given the MJO status at the time. But we have quite a bit of model predictions that were started up in the late 2000s as part of the US CLIVAR activity, then later the MJO Task Force, which I was a member of, where we applied the methodology, RMM methodology already introduced by Zane, to a number of our operational modeling centers in the European, for example, the CFS, the GFS, and so on. And this is just an example of the RMM index, the observations in black, and then the forecast and with the various ensemble numbers from the European for this particular forecast case shown there in the upper left, indicating at least with this model and this guidance during this time of the this particular forecast period, the MJ was expected to maintain itself and propagate eastward at a reasonable clip from the Western Pacific into the Western Hemisphere. As I mentioned, other factors include equatorial waves, and we have a number of different products that we make use of, and working with Carl Schreck at the University, in Nashville, where he works with CSIS there. He calls into our conference calls and provides a lot of information and support, as well as his thoughts on the current situation each week. And these are just two examples of low-level winds observations and in the forecast mode that we make use of to try to focus and identify these other waves that I mentioned that do have impacts on the tropical rainfall patterns and potential tropical cyclone development as we move forward over the next 1 to 3 weeks. And in addition to all of that information, we certainly have the raw model guidance in fields such as vertical wind shear, precipitation, and so on, and we collaborate quite extensively with other operational centers, for example, the Joint Typhoon Warning Center, the National Hurricane Center, and so on, with respect to producing the outlook. So in moving to the second section, just 2 slides in this section, and I just wanted to note the 2 major changes include just converting the outlook that I showed previously to an objective probabilistic-based outlook that will be can still be modified by the forecaster, but this will provide a much more rigorous first guess and also in a probabilistic format. And as I mentioned, shifting it from weeks 1 and 2 to the week 2 and 3 time period, as it aligns more appropriately with the CPC mission. And to support these changes, objectively derived probabilities, dynamical models, and other statistical hybrid type forecast tools are used to inform the new GTH product. And the conversion of this really adds a nice depth to our potential climate integrated decision support services that we use the Weather Service, improved opportunities for that, for pivotal impacts related to tropical link phenomena, not only TCs, but also monsoon breaks and surges in the Southwest US, for example, and other areas across the globe, of course, atmospheric river events, and so on. And moving in this direction is really key for CPC and the Weather Service and NOAA, as it targets out areas in which the Weather Research and Forecasting Innovation Act of 2017 really wanted it to work on advances towards extending outlooks of extreme events further into the subseasonal timescale, as well as applied research targeting tropical cyclone activity in general. So this slide shows, to first order, what the new product map will look like. There's a number of different shapes on here, more to help illustrate some of the variability and how the map will look. But you'll see in the legend, these are probabilities at various ranges: 20 to 60% for tropical cyclone formation probability, 50, 65, and 80% for temperature and rainfall probabilities down on the bottom legend there. Again, shifting from week 2 in the top, from week 1, and to week 3 from week 2 on the second plot. And this is, there'll be maybe some tweaks with this as we move forward, but this is the general plan at the current time. So moving into the last section, some of the research and results we've had so far as doing this. First, with analyzing the reforecast precipitation data from 4 different ensemble modeling systems, the European Center, the new GFS version 12, the CFS, and the Environment Canada ensemble system. And what's shown here on the left is week 2 precipitation, and week 3 on the right. And this is for the December, January, February time period. And the numbers in the upper right show the 30 south to 30 north average, but of the anomaly correlation. But the color bar to the right there shows what the shading is in each of these plots. And really what I wanted to show is, the first order, you can see that in the tropical areas where we're doing this particular outlook, there's modest skill. You can certainly point out the ENSA regions as well as the known hotspots for MJO activity in most of these model forecasts in week 2 and even into week 3. But you also see areas, for example, in the European in the upper left, significant anomaly correlation north of the equator towards the west coast of the U.S. That's evident both in the European and the GFS. Again, these anomaly correlations are modest at reaching out greater than 0.5 in some of the yellow areas. But keep in mind, this is overall over the whole reforecast periods. And so forecasts of opportunity can be considerably higher given certain circumstances. One thing we also notice in these particular plots that the GFS are shown in this analysis is pretty close to our own part to some of the European data that are shown here, and where the CFS and the Europe Environment Canada forecasts are a little bit worse in skill, again, as measured in this metric and application. We have real-time plots that are shown here of correlations with CMOR precipitation data, satellite precipitation data over the past 60, 90, and 180 days, for these four particular modeling systems to help us get a gauge for how the models are doing as part of various seasonal cycles and in real time. And so what you can see here, the blue blue pluses, for example, is the European. Again, this is weekly precipitation verification against CMOR satellite precipitation data. And those generally are ranged and score the highest both in week 2 and in week 3. As far as ranking them, the GFS version 2 does quite well. Is the secondly ranked model out of these four particular systems, again, with this application and data. And it scores quite close to the European in many instances. The CFS seems to have more dropouts or lower skill periods, at least in this short record here of 180 days. So we use this information to just get a handle on how the models are doing in week 2 and week 3 to support the forecasters. And I also will note that even though the verification anomaly correlation has a certain value as average over time, there's certainly periods where there is clearly forecasts of higher scale depending on the situation, as noted earlier. As far as products that are produced, we have a whole range of them from the different modeling systems, as I mentioned. What's shown here are forecast probability maps from the CFS, European, Environment Canada, and the GFS for weeks 1 through 4. We have them. The one on the right is an example for week 2. And the possibilities that the forecaster has are shown in the upper left there, anomalies from the forecast ensemble systems, their probabilities. And we also have the consolidated forecast, for example, which is shown just below that, where that consolidation is based on historical forecast skill. And that the consolidation weights for the 4 different models are also available. They're not shown here. But we have this for weeks 1 through 4. And for different thresholds, we currently use the upper third and lower third for the product now. But we also have these forecast guidance products for the top 10%, 20%, and the terciles. As far as how the current real-time skill is for these particular precipitation forecasts, what's shown here are Bryan skill scores for 2 years. We haven't updated through 2021 yet, but this is from just the winter season to focus it down to 2019 and 2020 for the CFS, European, and the Canadian. And the consolidated forecast, we didn't include this for the GFS at that time yet. And one thing I'm just focusing on the left-hand side for the above normal category. A few things to point out is that there seems to be pretty good granularity and variation between week to week with respect to some of the subseasonal modes in the European, which is the cyan bar, where the Bryan score is highest in week 1, but those then drop down in week 2 and week 3. Other models, for example, the CFS seems to be much more level, which may indicate that it's more focused on some of the lower frequency variability for its forecast skill. The other thing that I would point out is that the consolidated forecast does perform the best at all the weeks, which one would expect given we're basically weighting it against historical forecast skill to get, quote, a more optimal forecast for precipitation. And generally similar results for the below normal category shown on the right. Moving to tropical cyclones with respect to how we're moving forward in tool development to support the outlook in this area. This is work that Lindsay Long, of course, has been doing for a long time. She's used the IRI-based Camargo and Zodiac tropical cyclone tracker and applied it to the dynamical systems we have, the CFS, of course, first, the European, the Environment Canada, and also now recently the GFS version 12. The forecast tracks use a number of different variables through the atmosphere. I won't go into the specifics of that, but we are able to track those, come up with a track anomaly based on historical conditions. And we also can calculate false alarm climatology to try in some ways to bias correct the real-time forecast for ourselves. And again, we have that for all the 4 models. And what we're trying to move towards is an example of the forecast period from later September into early October, where we're taking a look at week 3 on the left. And this is hard to see, I understand, because of the 4 different models, and it's the whole global domain. But if you just focus in the Atlantic sector, for example, if you look at the week 3 forecasts for the different models, the CFS is in the top, GFS in 1 row below that, and the European below that, 1 row below that. You can see generally activity and tracking are shown with the CFS and GFS. There's stronger storms that are anticipated in some of the ensemble members from the GFS version 12, which would be expected due to somewhat higher resolution. But one thing you'll notice as you go in that period, there's general consistency for more of a Atlantic recurvature pattern as opposed to the Gulf development. And as you go further into the center column, for week 2, you can see that is a little bit strongly indicated by all the modeling systems, except maybe perhaps the Environment Canada on the bottom. And you can see some of the kind of convergence, if you will, in the just east of the islands in the central Atlantic. And then as you go into the week 1 forecast, which would be for the same period, but of course, another number of days further out, you can see how things really tighten up and become much more clear. 2 particular systems, for example, in the Atlantic Basin, 1 more in the east, and then 1 more beginning just east of the islands. And you can kind of see that with most of the model guidance. So the idea here is to provide some heads up on the potential areas of favorite development based on a convergence of evidence, if you will, from dynamical model support, statistical tools, as well as our own understanding of relationships between the MJO and tropical cyclone development moving forward, beginning in week 3 as we move forward into week 1. As an example of that, this shows a forecast where we've done experimental probabilistic tropical cyclone genesis and track guidance tools based on, in this particular case, based on the dynamical model ensemble prediction systems. And you can see that from the color bar, it's consistent with our general outlook, new outlook format, 20% risk, 40% risk, and 60% risk, which is the blue. And the top plot is a combination, if you will, of the 3 forecasts. Again, this is just for the 3 of the models at this particular time when this plot was made. But we also now have this with the GFS. We have 4 models in which we're able to produce a consolidated forecast or multi-model ensemble forecast that's shown in the top row, for example, where we hope to highlight the most likely hotspots based on a convergence of evidence in the model guidance, but also with other known factors. As far as the historical reforecast scale, which is shown here, this is just the hit rate and false alarm rate for the 4 modeling systems. This does include the GFS, which is in the 1 row from the top. The hit rates on the left, the false alarm rates on the right. And this is, again, this ranges from 0.1 to 1 in the color bar down below, and 0.01 to 0.3 for false alarm rate on the color bar on the right. And I don't have time to go through all the details that are shown here, but one thing I will note is that generally across the board, the forecast skill in week 2 and also in week 3 is lower across much of the Atlantic Basin, Gulf of Mexico, very diverse basin, many different ways in which development can occur than, say, the Eastern Pacific. And you can see that with brighter yellows and reds across the Eastern Pacific for most of the model guidance, and generally less so in the Atlantic region for the hit rate. One thing I will note also, at least in this particular range of data that we've had, there seems to be somewhat of a higher false alarm rate with the new GFS version 12 across parts of the Atlantic Basin. We need to look into this more to confirm this, but that's one thing we have noticed in these plots, and also for other areas, other basins so far. But again, we've just started working with the GFS version 12. This is also relatively high for the CFS. I would say the European model has probably the lowest false alarm rates overall as well as perhaps the Environment Canada forecasts in most basins, I guess. Moving on to, so that's false alarm hit rate. So you have to be careful with false negatives or hitting correct no forecast. So we want to make sure we do some metrics targeting extremes. We use the symmetric extreme density score, or SEDS, which is trying to focus more on the higher end extremes. This is for week 2 and week 3. Again, the same model structure on the left: CFS, GFS, European, and Environment Canada. Week 2 in the first column, week 3 on the right column. And it's a little bit different way to think of that. Anything below 0.5 is basically not skillful in any way. The purple area there. It's as you get further up past 0.6 and some of the greens and yellows where you start to have fair and good skill as measured by this type of metric. And if we're to focus on week 2 and 3 for, say, the European, which tends to have the highest skill in using this metric, not everywhere, but in many areas, especially the Eastern Pacific, for example, you can see in the third row across much east of Hawaii and then towards the Mexican coast, but also significantly high for much of the Atlantic basin. The scores, of course, the metric also, of course, is lower as we go to week 3, of course, with all of the guidance. But still, I would argue, still some significant potential for heads up, even at that time range, given certain conditions and agreement and model guidance. The GFS, I think, does very well in the Eastern Pacific, as I mentioned, comparable to the European Center, version 12. But I would say, again, is a little bit less skillful across parts of the Atlantic Basin overall, as measured by this particular metric. The last slide I want to show is some of the forecast guidance products that we're working on. We're trying to do other approaches than just doing the tracking. This is a relationship between typical large scale. It's more of a hybrid type technique where we're using large scale dynamical fields that we know are important to tropical cyclone development, SSTs, the vertical wind shear, for example, sea level pressure, things like that. Of course, I'd have to get exact list from Lindsay, but those sorts of things, and relating them to producing probabilities from the 4 different modeling systems based on observational tropical cyclone genesis and tracking data. And we have these pie charts, which are a different way of looking at things. These are for TC activity, or basically TC days during the week, where we compare that to the normal category for that particular basin. We have that for the Atlantic and Eastern Pacific as an example here on this particular figure. Atlantic Basin on the top row, the Eastern Pacific on the bottom row. And we calculate the probabilities from the different models for either being a near normal or below normal or above normal for that particular week in TC days for each of the 4 models, which are shown on the top there, the CFS, European, GFS, and the Canadian. And then we develop a multi-model ensemble based on that. And so we're still working on this. And in fact, we're just in the process of doing the long-term verification. So I don't have that sort of information for you here today, but we are looking to see how this does. We want to do something like this as a complement to the dynamical model tracking that we have as well. So that we have a number of different tools to support the new Outlook format. This is just as an example for week 2 for this particular slide. And to wrap up the last slide summary, CPC operationally releases the Global Tropics Hazards Outlook each week. It targets precipitation temperature, as well as tropical cyclone, potential tropical cyclone development areas and associated impacts currently for the week 1 and week 2 time period. We are working with SDI support to convert that product to probabilistic format targeting weeks 2 and 3. We hope to experimentally and publicly release this sometime during fiscal year 22. We are working with partners and our collaborators to ensure that they are comfortable with this and how best to perform the required outreach for this change. And again, with SDI support, we will have and will continue to do forecast evaluation of a number of different forecast products, whether it be dynamical model guidance on precipitation and tropical cyclones or hybrid type techniques using the different systems that we have from international operational ensemble prediction centers, and both in the real forecast mode as well as real-time perspective. So I thank you very much for your time and your attention, and I'll try to answer any questions I have. Thank you. Back to you, Vivi.
Thank you, John. Great talk again. So I don't see any questions on the discussion forum, but if anyone has a question, if you'd like to type later, we are going to follow up with John. And so to get a response and we share with you all. So it's already 3 p.m. So I just want to make an announcement. Our next webinar is going to be on November 1st. And we are going to have another machine learning talk, and one talking about improving S2S precipitation forecast in UFS. And then another talk on predicting Indian monsoon onset in S2S scale. So have a good day, everybody, and thank you so much for coming. Hope to see you next month.